Now, let's see the very unique property of benzene. As we already know the real structure, now we would like to learn that benzene is actually a nucleophile. A benzene ring is nucleophile. As you can see here, there are 6 p orbitals here. They overlap together forming pi bonds. But in this case, all the 6 p orbitals overlap together and make a pi bonding system which forms like a ring here, above and below the ring. So this mechanism or this system is what we call the pi bonding system or delocalized system, right? Due to this has a very high electron density, which makes benzene ring as a nucleophile here. So as you see here, this is the definition for electrophile. This one is for nucleophile, and benzene ring is indeed a nucleophile because it has a very high electron density to donate a pair of electrons. It is basically rich in electrons, right? Okay, now going to the reactions of arenes. So reaction of arenes, what's so famous in reactions of arenes is this one, electrophilic substitution. As you can see here, electrophilic substitution, not only that, but also the non-electrophilic one, like the normal ones, basically the normal reactions a compound would undergo. I will give you the list for electrophilic substitution. There are 5 here: halogenation, nitration, alkylation, acylation, and sulfonation. 5 of these have the same basic mechanism. So if you already understand the mechanism in electrophilic substitution of benzene, then you can nail all these 5 reactions. But how about the other reactions, the non-electrophilic one? This is basically just the normal one. I believe you have seen this ordinary equations or reactions: oxidation, combustion, hydrogenation. Now I'm just going to focus on this one, electrophilic substitution. Here, electrophilic substitution basics. Again, as you remembered before, benzene is a nucleophile. That's why the name is electrophilic substitution. Why not nucleophilic? Because there is an electrophile attack. If there is a nucleophile attack, we call it a nucleophilic mechanism. But since benzene has a very high density, so it doesn't need a nucleophile again. It needs an electrophile attack to react, right? Because they are too rich in electrons, so they want to be generous and give away the electrons. That's why I need an electrophile attack, and we call it as an electrophilic substitution. Why substitution? Because the hydrogen will be substituted with other functional groups. Okay? That's basically it. That's like the principles for this electrophilic substitution. So the mechanism is first there, see number 1. So there's an electrophile here. It is like sign, it has a sign positive because to show that there's an electrophile attack. Because there's an electrophile attack, the benzene would be too generous to give the electrons away to the electrophile. Instead, they will form like an intermediate here. Don't forget an intermediate where the delocalized system will be disrupted. That's why there's a positive sign here, because it will make a covalent bond with an electrophile and also with hydrogen. But since this is a substitution reaction, again electrophilic substitution, so the hydrogen needs to go away, right? Needs to say goodbye. That's why to regenerate the delocalized system. So if you see here, so see, hydrogen needs to give the bond between C and hydrogen here, needs to give the electrons to the delocalized system to regenerate the system again, but instead hydrogen need to say goodbye. So there's a substitution happens between hydrogen and electrophile. Before, this is hydrogen, now substituted with electrophile, like that. Okay, and yeah, basically this is the basic mechanism. Also, don't forget about directing effects. So directing effects is when, you know, when benzene is already connected or bonded to one group, and that group in which it is bonded to will direct the incoming effect. For example, in a simple scenario is, for example, like this, nitrobenzene, right? Nitrobenzene. So this nitro group, if there is another group, let's say group A want to react to benzene, but this nitro group will control the group A, the incoming group A. So nitro group will say like, I think group A, you should go to carbon number 2, or you should go to carbon number 3. That's why nitro group will control which position the incoming group will go to in the benzene ring, right? That's called the directing effect. There's an electron donating groups which will direct that to 2, 4, and 6. Electron withdrawing groups which will direct incoming group to carbon number 1, 3, and 5 in benzene rings. That's basically it. This is the table. If you want to memorize, feel free to memorize. And then this is the reaction for halogenation. Just replace the X before to halogen. And then this is, the reactions. This is nitration. Just replace the X with nitro group. As you can see, NO2 plus, not X anymore. And then there is also an equation to prepare an electrophile, because we cannot directly get electrophile just out of random reactions, right? We need to prepare like a reaction to prepare the electrophile. Same goes to this electrophile in halogen. And then this is nitration. This is acylation and alkylation at alkyl or acyl. That one, and sulfonation